And let's change gears here to our lecture. So, I guess we're going to get started. I imagine more questions will come up as things go on. We're still sort of in the thick of the COVID time, so you know, confusion is bound to happen. That's why everything's recorded. That's another thing. I got to be honest, the students last semester seemed to really like the recordings that I already had, and they thought that they were really useful as far as going back and looking at things. Now you just get to view them and then go back and view them. But again, those will probably be up tomorrow sometime in the afternoon. If I get lucky and things work out, they'll be up tonight, but I'm not sure that will happen. But basically, the whatchamacallit, they're just like this. It'll be like you hearing me, talking to me, watching me right on the screen. And like I said, based on the amount of questions I got, which wasn't a great deal, you know, it'll almost be like most of you, it'll be almost indifferent than if we were actually doing it live. The thing is it'll be nice because we'll have a space for interaction. And like I said, the point of the, even though I'll be talking a little bit on Thursday about the labs, the point really is to be as interactive as possible with that time. So that's the time where you always should just jump in with a question, and you know, as much as you want, because that's really what the goal there is to leverage our interaction, whereas here you're just looking at the lecture. But okay, so let's start our Physics 1 journey. I hope we got out of it all the way. I'm sorry for sort of just barreling into it. Like I said, I started at 9:15 this morning, so I guess I should tell you a little bit about who's this crazy person who just sort of told you all about the course and how short the semester is. So anyway, again, Professor Toland, that's me. Hi. I'll put on the video. So I've been at LaGuardia for, this is my 8th year, I think. I've been at LaGuardia long enough. I'm not quite sure how long I've been at LaGuardia. I started in 2012 though, so yeah, good, 8 years, yeah. So that's right. But I don't remember just offhand. So I've been teaching physics at LaGuardia for 8 years. I've been teaching physics in one capacity or another for 15 years, and I've been studying physics for 20 years. So my specialty is in quantum physics, and I do research on quantum devices, designing and devices that use the quantum properties of matter to measure new and interesting things. So, and this is, I have an ancient webcam, so that double thing will eventually fix itself into one image very quickly. I have loved the idea. I've loved physics almost, I guess, half my life now. I've been studying it, but I've really, you know, I got into it through studying science fiction, and I've always loved the subject. I didn't realize what it was called when I first started doing it, but it's really fascinating. And I think the thing to keep in mind with physics is that even though I know a lot of you are engineers, sometimes it can seem a little abstract for what we're talking about. Well, I hope I don't have a twin. That would be I'd lose half my prime rib on holidays. But the beautiful thing about physics, even though it can seem abstract, and I know a lot of you are engineering students and computer science students, and I do want to let you know we do have a physics major now at LaGuardia. It's new, so that's why your math people didn't know about it, or other people, but we actually have a chemistry and a physics major. If you're interested in those two things, you should send me an email. That one I will get back to you on, or a Skype message. But the beauty of physics is it sort of sets up the rules really fundamentally for how the universe works, right? What's allowed, what can we do and not do in this universe, and what are the rules of the universe? And we really, it's fascinating because we don't really understand everything about the universe. It's still very much, it's a living field. There's all sorts of things going on, all sorts of new discoveries. And it's just really fascinating. One of the things I like doing at LaGuardia is that I've gotten into, well, because we have a scanning electron microscope, is sort of experiencing the world at regimes in either temporal or visually, on time scales and length scales that we don't interact with normally. So I got into that with this scanning electron microscope, and like zooming in on a screw, and it looks like a Martian landscape is pretty cool. I would also direct you to, and probably during our discussion times, I'm going to bring in some YouTube videos, particularly from this channel I've liked called the Slow-Mo Guys, which I recommend checking out. It's a lot more applicable to physics too, but there's some pretty cool stuff there. But just seeing things slow down and seeing how the dynamics of things is really incredible, and I think you engineers would like it, that channel in particular. But it's really studying this subject is about trying to get a handle on the universe and the rules that allow things to exist the way they do. So even though we sort of get from that abstraction and that cutting edge and come back down to mechanics, which is the basis for that structure, it can seem a little dry, but it really is the basis for a way of thought that's very incredibly powerful. And I would say that the deeper you can understand physics and math in your engineering, the more dynamic you'll be in your problem-solving ability and ability to think. So hopefully, as hard as everything might be, that's some real motivation to really dive in and make those 6 hours a day exciting, because they really can be. I'm hoping that the problems push your brain into ways you haven't thought of before, and that's our goal. That's really our goal here, is to push your brain a little farther than you've previously gone before, to think in a way that you might not have thought before. That's what I really want you to do here. That's the goal. I know I have a lot of course outcomes in there, but that's my intention. So the first thing we have to do is sort of understand our rules of science. So when we're in science, we sort of have, and in physics, you'll often have these two branches, experimentalists and theorists. And one of the beautiful things about science, and people are trying to fight against this idea, so you got to be careful, but I would still maintain that people dismiss it under the guise of other semantic arguments, but science is ideas that are beholden to experiment. All right, a good and powerful scientific question is one in which you can pose an experiment that will give you insight into your hypothesis. All right, so sometimes we call it falsifiability, right? At a freshman level, we'll say, oh well, you can disprove yourself. You can't prove yourself, but you can disprove yourself or eliminate something, and that's part of it. That's what we do, but a lot of the limits of what we can look at have to do with how we measure things. All right, the measurements we make define the limits of our experiments, and that's what gets us fundamentally to our chapter 1 of measurement. All right, everything we do is an expression of measurement, even our theoretical calculations at this point. So it's stuff that seems easy, but we're going to see some problems that are kind of exciting that will challenge how we think. Okay, so let's hop to it. So the rules for measurement, right? All this beautiful stuff. So we will talk about the things physics, it has this word that deals with physical, right? We want to develop this idea of what's physically going to happen. So basically, if I push this pen, what will the motion happen? What will the motion look like? How will the pen behave? If I push it harder, what will happen? All right? And this will also extend to mathematical ideas. We'll define things very rigorously. I'd like to think very rigorously. The mathematicians might not agree, but we'll have definitions that may seem different than they've previously been used. And so we want to be very careful how we use things. One of my mentors in graduate school told me that half of physics is bookkeeping. So we're going to need to do that. So let's take a look at a scientific number. I do this in astronomy, although here you will be responsible for the math. And I hope the pen doesn't work as well this semester as it does last semester. I don't really know how else to say it. But let's just write a number. 6 times 10 to the 3 meters. Okay? So we have here our units This is what we're learning about first. Our unit will tell us what kind of quantity we have, right? The number is not enough. Are we talking about length? Are we talking about forces? Are we talking about energy? You got to be very specific and say what unit you have. Scale will allow you to compare very easily, right? Are you, if you're looking at length, at meters, right? People are about the scale of 10 to the 0. School buses are about 10 to the 1, right? Buildings are about 10 to the 2, like the Empire State Building, things like that. So you start to use that. You can define objects at that scale. So this one we'll call scale. I'm thinking maybe the tip is broken on this. I don't know. I've been playing with the pen all day, and I've not had very good luck. So you'll have to excuse my rambling. The last one here, these numbers here give us the precision. So usually we call these the sig figs. So I'm gonna spill the beans on the magic. 3 sig figs is fine for the course. That being said, when you're doing a measurement or talking about lab, I do tend to be, the rule for sig figs is that your calculation is only as strong as your least known quantity. Whatever you're doing, that's your sig fig. It's supposed to be an expression of precision, right? If you have a really precise measurement that gives you 10 sig figs, and there are measurements like that, you have to express them all. But it doesn't make sense if you took the square root of this number, for instance, which would be an irrational number, to write 1,000,000 digits out at the end of the calculation. You just sort of estimate based on your weakest known quantity what that precision should be. All right? So I think we're good there. So it says here there are many different physical quantities, but not all are independent. We are going to see we have a lot of compound quantities. So there are base quantities, right? So it says here there's 7 fundamental quantities such as length and time. 3 of them are needed for mechanics: length, time, mass. I'm guessing charge is another one, and they probably come up with other ones as well. All have been assigned standards, and all are used to define all other physical quantities. All right. So this is true. Like if for those of you who are a little older, you might remember like the meter used to be and the kilogram used to be defined in terms of these standards that were in Paris, in France, but now they're defined in terms of they're defined in terms of fundamental constants. So that's what they mean by base quantities. And then you have composite quantities like speed, right? Speed or velocity. Velocity is equal to meters per second, right? So you can see how that's a compound unit. So base standards are required. They're required to be accessible so that precise measurements can be taken, and invariable, which means they don't change over time. And this is actually an interesting property. There's a lot of experiments to determine if certain quantities are base quantities, to see if they change at different points in the universe's history. So this can actually be a really interesting question about these base quantities. All right. So we will be using the SI unit, the International System of Units, which is it's basically the metric system. For those of you who have not grown up outside this country or experienced education outside this country, the metric system may seem weird, but it's based on the number of digits you have. All right? The imperial system is based on the opinion of some British guy or someone who hated some British guy, and weird things happen. It doesn't make a lot of sense. But before you hate on the metric system, it's just based on the number of digits you have, which is 10 for most human beings. So the base units for length is the meter, for time is the seconds, and for mass is the kilogram. All right? So again, I called them compound units, but I like this word better. There's many derived units. I want to see if I can... No. Pencil. I just want to see if I can change the width of the line. It's not cooperating. This line is just too thick. But we have the derived units, right? Like we saw for speed with meters per second. Underline derived again. So joules and watts, you can see how you have 1 joule is equal to a kilogram meter squared over second squared, and a watt is a joule per second. So you can see that any unit can be done in terms of base units. Now, I had a friend who, when we were undergrads together, this was way back in the early 2000s, he actually got his whole physics degree by figuring out things with unit analysis. So he would figure out what he had to do, what operation, what math was needed, by just looking at the given units of a problem and then seeing what you'd have to do to get to the final units. And he did pretty well. He teaches it out over in the West Coast. But using unit analysis solely is one way to approach the whole course. So are there any questions so far? Some of this is the scientific notation part. We'll go over that fairly quickly, but any questions thus far? Everyone good? Okay. All right, no questions? All right. So when we look at scientific notation, right, it again, this makes metric make sense. We use these powers of 10. So I think you all, by this point in your scientific careers, know that you don't want to write 3,560 million like this. You'd rather have this compact way of writing it, right? And you'll notice you have, again, the units, the scale, and the precision. All right, very nicely stated. Now, what you want to notice, and what I feel like I should say, is you'll notice that when you have 10 to the minus 7, it's not a negative number. I know we're not in astronomy, but you'll have to forgive me. I'm just coming from there. And so we have that number of zeros before we get to the 4, right? So you'll notice we get, the 4 is in that 7th decimal place. So we can express both very small and very large quantities and know what kind of precision we have all in these compact scientific notation statements. All right? And of course, with unit conversions, minutes to seconds, there's 60 seconds in 1 minute. So 2 minutes, the minutes cancel, you multiply, you get 120 seconds. I think you've all done this and can see this, but it's good to see again. All right. Now, this is one of those things we have to deal with, and I just want to make sure that we're getting everything. So I'm going to open my my thing. So this here shouldn't be like this. It's just it's an error of the conversion process. So I just like to make sure I have everything, all my ducks in a line. So so when we take measurements, right, we talked about definitions. So the need for accuracy in science and the development of precision measurement has changed the definition of these standards. So just for instance, we'll do the meter. The meter used to be 1/10 millionth the distance from the North Pole to the equator, right? That was defined as the meter. And then we had that standard meter bar kept in France. And then for a while it was, up until about 3 or 4 years ago, it was this fractional wavelength, the exact number of wavelengths of an emission of kryptonium-86. And today, the meter is the length of the path traveled by light in a vacuum during this specific time length. So basically, the meter is defined in terms of the speed of light, okay? And they're all sort of interchangeable in this way. And the speed of light is interesting because that is a fundamental constant of the universe, and it actually is the same regardless of the velocity you're using to measure it. And we'll talk about that when we get to chapter 5. The speed of light's a funny thing. So in each transition, the new distance was chosen so that the approximate length of 1 meter was preserved, right? That's the other thing. So the meter is not unfamiliar as each definition changes, but each definition allows for more precision to be obtained. And that's important. Okay? Now, some lengths that I thought would be fun. We can see the distance to the first galaxies formed in meters is 2 times 10 to the 26th. We can get all the way down to the radius of the Earth is about 6 times 10 to the 6th meters. We get down to the thickness of the page of a book is 1 times 10 to the minus 4th meter. The length of a virus, which is useful for if you're wondering, if you think that your mask will somehow filter out coronavirus, you'd have to have grid meshing lower than 1 times 10 to the minus 8th. That might be ambitious. The radius of a hydrogen atom, No, you won't have to memorize. Oh, yeah, no. So my recommendation, so I can't stop you from using your book during the exam. I'm not that naive. I will tell you this, that it's a terrible idea. So if you were in class in person, I would let you make a sheet of 1 page for one side. So because I can't leverage the sheet length either, I would suggest that on no more than one sheet of paper, you write down all the things you think you'll need for the exam. Because when you do that, you'll be familiar with them. You won't depend on them being in the book. And two, you'll find them and know what they are immediately. No. I am not. This is in science as STEM people. I do not value much on memorization. I don't put much stock in it. I expect you to create your own resource that's usable for you to adequately answer the exam questions. Some things you want to know. You're going to want to know that 1 inch is 2.54 centimeters. Some of this stuff is if you need some of this stuff on a question in this class, almost all of it will be given to you, or will be available in a table in like the back of your book, or something like that. Yeah, no. You shouldn't need to memorize. We're here to understand, not to memorize. So yeah, don't freak out about there's a lot of stuff you should freak out about. Memorizing a bunch of stuff isn't one of them. Not at all. Okay. This is supposed to be interesting, right? So you get to see the range of the size of a proton all the way up to the size of galaxies. I probably will. I don't know. I think I do. I have to check. I'd say if I'm covering it, expect it. That's usually my thought on it. The test would be about converting a unit. So what you should memorize is that there's 1,000 kilometers or 1,000 meters in 1 kilometer, and 1,000 kilometers in 1 megameter. You probably should know that, but that's easy stuff. All right. So significant figures we talked about. I'm gonna just pause on this slide and let you read it again. You'll notice when they're just talking. I feel like what I said is the important part of sig figs. I feel like the rules sort of take away from it and just get you confused. So again, if you have two quantities and you're doing any operation with them, the result is only as strong as the weakest link. Basically, all of this crap here, where they're giving you all these rules, it all really boils down to this. This one obvious thing. Question mark plus 5 is equal to question mark. You don't know, right? Question mark times 5 multiplied by 5 is also equal to question mark. So, for instance, if you want to know, if you have, say, 1.3 and then 2.5632, and you need to multiply these numbers together, you can write this as question mark, question mark, question mark, and then you can add or multiply, and whenever you have to multiply or add the question mark times something, you don't know. You're always going to get the right number of sig figs if you keep that in mind, without rounding up or down or however it is. You can, it'll just come out. So that being said, that will answer your relevant questions for sig figs. I think they make this overly complicated, and I'm not into it. So the first thing I want you to try and work out, and so you'll notice that again about memorization, see if you can do these conversions. These are two examples I really like because they're not intuitive. So if the universe is 13.75 billion years old, what is the age of the universe in seconds? And then convert 1 meter to cubic centimeters. All right? So you know that SI is in seconds, so you want to figure out how many seconds are in 1 year, right? That'll be something you want to figure out there. And then converting 1 cubic meter to cubic centimeters, that's interesting. Let's see what you get there. I have to address those. So give it a try on your own. I'll give you about three to 2 or 3 minutes, 3 or 4 minutes. No, I'll give you 4 minutes. I'm going to go back here and sit in my air conditioning. I'll tell you one nice thing. Well, I guess not everyone has the same air conditioning because the rooms are hot. Good. That's about right for the, I was saying that's good. That's about right for the seconds in the universe. So some of you might be asking, how did he do it? And some of you might be going, we know how he did it. So let's take a look. Good, Li Huan. So let's take a look at how we arrive at something. So the question is, how many seconds are there in a year? Well, we know that 1 year, in 1 year there's 365 days. In 1 year. And we know that there's 24 hours in 1 day. And we know that there's 60 minutes in 1 hour. And there's 60 seconds in 1 minute. And you'll notice that the units, we can see the units cancel very nicely. And all we have to do is multiply this, will give us the number of seconds in a year, and we multiply that number, the number of seconds in a year, by 13.75 billion, or 1.379 times 10 to the 10th years. And then that will give us, if we do seconds in a year, that will give us seconds. And then we get that 4.43 or 4.33, 4-ish times 10 to the 17th seconds. So that's what you should get. So any questions on that? Does anyone want further clarity on how we got there? No, we have seconds right here, right? It's not written well. Again, hold on. I'll write it. I'll try and write it cleaner. It's hard though with the pen length like this. I'm gonna have to see if I can find new tips. This is. Let's see what if I. This is just odd. Okay. Oh, right. No, both of you should have had units. Both of you should have had units. But that's okay. That's okay. So remember those seconds in the future. Now to look at the convert for the cubic meters, I think you've got it. So we'll want to remember we're looking there that 1 meter equals 10 to the 2 centimeters. So 1 cubic meter is 1 times 1 times 1, and then that'll give you 1 meter cubed, right? And then so we just plug it in, times 10 to the 2 times 10 to the 2 equals 10 to the 6th, and that'll be centimeters cubed. Okay? So make sure that makes sense. It's important that that makes sense to you. I just want to be sure before we move on. So take another minute, look at it, make sure we're all on the same page. Okay? All right. Let us move onward and upward. So now we're going to talk about some of these base units. So now we will talk about time. So time is real easy to get groovy about. And what I mean by is like, what is time? Is time a man-made concept? Does time exist? The answers are yes and yes. It is a man-made concept, and yes, it exists. Time is a counting quantity. All right? Any standard of time needs to be able to answer these two things. One, when did something happen? And what was the duration of the event? And that's all time does. Time follows the same conversion process as lengths. So standards of time in the past have included rotation of the Earth, quartz vibrations, atomic clocks, cesium atomic clocks with time signals sent out by radio. And today, 1 second is the time taken by this exact number of oscillations of the light of a specified wavelength emitted by a cesium-133 atom. All right, that's the most precise measurement we have. Now, what's interesting about this is as you try and wrap your head and say, well, that's not real time, keep in mind that basically this is an atomic transition. You're looking at the frequency of an atomic transition. Every process you can think of, cell degradation, cell replication, you touching something, you interacting with something, is some sort of atomic interaction. All right? So the fact that time is based on a elementary interaction or a number of oscillations of an atomic interaction, an atomic frequency, it's pretty solid way to count something. It's not arbitrary. I mean, it seems arbitrary, but it's based on the building blocks of the universe. So, you know, atomic interactions guide your existence. Well, I don't know about guide is the right word, but they create the background of your existence. So basing time on them is not a terrible idea. And again, this will ultimately be able to be defined in terms of h-bar and length and things like that. Now, I don't like to talk about this one because this is physics fantasy, and physics is not without its fantasies. I was sort of implying that atoms guide your existence, whereas atoms really make up what you can and can't do in your existence. I didn't think guide was the right word. But the lifetime of a proton here, right? This is predicted, but no one has ever seen a proton decay ever. So I'm kind of a stickler for I won't believe this one till I see it. It's a good hypothesis that the proton decays, but you got to see one. And you'll notice that this number is much, much bigger than the age of the universe, which you all just calculated, and this is about right, 5 times 10 to the 17th seconds. The age of the pyramids of Cheops is 10 to the 11th seconds. Human life expectancy, you get about 2 billion seconds. Enjoy them. I think I've hit about 1 billion myself. Length of a day is about 9 times 10 to the 4th seconds. Time between heartbeats, about 8 times 10 to the minus 1 seconds, or 1/8 of a second. Lifetime of a muon, that's a subatomic particle, is about 2 microseconds. The shortest lab light pulse is 1/10 of a femtosecond. And the lifetime of the most unstable particle is 10 to the minus 23 seconds. And the Planck time is 10 to the minus 43 seconds. Now, the Planck time is sort of where time is thought to pixelize into discrete little bits. We don't have, again, the shortest lab pulses, the times we can look at would be somewhere around here. So we're about 20 orders of magnitude away from the Planck time. All right. Now, I wanted to show you how time is measured and sort of to give you a visual. This is a slide I made myself. I'm proud of it. So we think of, you know, time, you can sort of see how the standards go. So I sort of look at this as past, present, or, you know, these are past. This is actually the present. If I think it's good for your soul to see what an atomic clock actually looks like. This is what the apparatus looks like, and I picked this one because they pump it with a purple laser. I'm a big fan of the color purple. But then we're starting to look at things like gravity waves and understand more about black holes. And so in the future, we may have more precise or different different ways of quantifying these quantities. And again, time actually gets affected by being near a black hole. So if any of you have seen that movie, I haven't seen it. I don't know if it's Interstellar. I think that's it. It's supposed to have some pretty cool black hole stuff, but yeah. So time has something to do with all the stuff here. You can look here with the atomic clock, the variation in the length of a day as measured by an atomic clock. So you can see that this is plus. Well, it depends what you mean by unsolved. We know a lot about black holes, but there's still a lot more to know. So what's going on inside of a black hole, that is unsolved. How black holes affect time near their event horizon, we're pretty confident on that based on the success of the general theory of relativity. So it depends. It depends what you mean by that. Is the black hole unsolved? But what we're looking at here is interesting, if far less so than a black hole for sure. But you can see here that there's the difference between the length of the day and exactly 24 hours in milliseconds. And you'll notice that you get these variations, this sort of variation back and forth through the years. And it averages out, it looks like here, to about 2.5 milliseconds. But sometimes we're right on. That's pretty good. And this shows the precision of atomic clocks and the relative imprecision of Earth's rotation, which can be affected by all sorts of things. So basically what you're seeing here is that you can see all these variations of the imperfections of the Earth's rotation on the atomic clock scale, which is pretty neat. So when you're looking at this scale, the Earth is a lot jittery. We can see it. So now let's get to mass. We'll sort of do the same thing with mass, and mass can be fun. So the standard kilogram used to be a cylinder of platinum. So this one was redefined in terms of Planck's constant and big G in May of 2019. And this book was published, this edition was published in January of 2019. So they missed it by 5 months. So this is not correct anymore. But it says accurate copies have been sent around the world, but there were discrepancies between copies. The atomic mass unit is a atomic standard, and 1 atom of carbon-12 is assigned the mass of 12U, and it's used for measuring the mass of atoms and molecules. And so now the kilogram can be done, the atomic mass unit can now be done in terms of the kilogram. And masses follow the same conversion processes as length and time. So we get to see some fun masses here. The mass of the known universe, 10 to the 53 kilograms, pretty impressive. Our galaxy, sun. Now you might be asking something. How do you measure the mass of something large? Like measuring the mass of a grape is easy. Even an elephant, you put it on a scale. But how do you measure the mass of an ocean liner or a small mountain? How do we get those masses? Well, for things like the small mountains and even the elephant, well, the elephant we can probably put on a scale. But for the ocean liner and the small mountain, we can use calculations of density and volume and things like that. And we can also look at the amount of total displacement of the water. The small mountain we probably use just from density. But we actually have tools, which we'll learn about at the end of the semester, that allow us to measure mass of large objects by looking at things orbiting them. So that's pretty cool and pretty powerful. But you'll notice you can get down here to grapes, specks of dust, and then you get down to heavy atoms and light atoms or protons, and then the electron is 10 to the minus 9 times 10 to the minus 31 kilograms. Okay? So that's what's going on there with the masses. One of the important quantities we will talk about is density. Now here the examples are they're stupid. And I say that because they're trivial. It's like given a mass and a v, you get the volume. We're in a calc-based physics class. The real power of density is not only that it's equal to mass over volume, but that it's constant. And because it's constant, that means that we can also say that this is equal to dm over d volume. Now, triple integrals are not something you've seen. You just evaluate them one at a time. But dm integrals are very hard, and it lets you make a dm integral into a rho dv or rho dx dy dz. This is much more manageable than this. All right? You're going to have to trust me on this. That's the real power of density in this class. And that's how we'll really use it to our advantage. In your lab, yeah, you're going to calculate this, but I do expect you to kind of look at this and go, yeah, I can do that calculation, all three of those. Okay, so now I want to get to, now that we've seen some basics, this is what I would consider a very difficult problem. A very, very difficult problem. I want you to, what we'll see as we do this problem, and I'm going to give you a full 15 minutes to work on this problem. Full 15 minutes. I'm even going to go away for a while, so I'm not tempted to talk over your thinking. But what you're going to see is that I'll read the problem and then I'll let you go. I'll let you start, not go, but start. We still have a lot to do. I'll let you start with this, but what I want you to do, or I want you to keep in mind, is the math to solve this is simple. It's math 115 math. But formulating it is hard. So let's read the problem. It's extremely difficult. In fact, my brother is taking a physics class this spring, actually, and he's been taking a lot of math, and I tried to explain to him the difference between math and physics and using math as a tool, and I gave him this problem, and he'd taken like 15 upper division math classes, and it took him a couple hours to solve this problem. Now, believe it or not, you guys are better suited to solve it because you already think practically. He used very abstract mathematics to arrive at the answer, and his solution was correct but very unelegant. When I showed him how to do it, he was like, ugh. A few of you will probably get it right, but again, when you're practically minded, you can make some sense of it. So let's read the problem. So let's suppose that while lying on the beach near the equator, watching the sunset over a calm ocean, you start a stopwatch just as the top of the sun disappears. You then stand, elevating your eyes by a height of 1.7 meters, and stop the watch when the top of the sun again disappears. So if the time elapsed is 11.1 seconds, what is the radius of the Earth? Your first thought here should be, huh? But I will tell you my hint to you before I let you go. This is a solvable problem. And my second hint to you is draw a picture. So I want to give you 15 minutes to struggle with this. I'll check back in with you all at 3. So I'm even going to go, because if I sit here, I'm just going to want to talk. You may have noticed I like the sound of my own voice. It's not great. But I'm going to check on some of the fires or email fires that have been on, and I'll let you solve this, and I'll come back and check on you, like I said, and we will go over this. I'm not just going to leave you hanging, but I want you to work on it independently and talk to each other as well. Okay, I'll see you at 3. Okay, so let's see what some of your questions are. Allow. Okay. All right, so let's see here. It is not a derivative problem. That's funny. That's what my brother thought as well. I think so. That's the only way I can think of, but still don't know how to proceed. Looks like. All right. So the first thing to do is to draw a correct picture. So we'll try and draw it, and I'll probably mess it up because I don't have straight lines. Well, actually, I might be able to do okay. So we're obviously not going to draw it to scale. So the first thing you need, oh, it very much is a trig problem. The first thing you need is to figure out what your quantity is. So let's get this circle. We've got to move it down here. The first thing you want to do is draw something that has what you want on it. So if you want the radius of the Earth, you're going to need the Earth. Now, of course, we're not going to draw this to scale, but we know that you're looking at the sun. It sort of sets. You're starting at one height. We'll call this one height. And you go here. We can call that R and H. And if we see the sun setting, I always mess up the direction for this. So if we see the sun setting over here, we need to make some auxiliary lines. Oh, that's where here's where I messed up. I don't need this line to be. I need actual straight lines. So I wasn't wrong there, but I'm getting tired and I really should have done this. So we have the center of the circle and we have our R plus our little h. Nope. That's the bad thing about drawing with shapes, is it often messes up. Okay, so let's choose a different color here. First of all, let's do some auxiliary straight lines. So I was starting with what I wanted, but I'm not sure that's going to help. Let's start with the givens. So I have this first auxiliary straight line, which is straight. No, I don't want that one. Delete. I need a line that is perfectly tangent. So I'm going to draw it as straight as possible. And then what I'm going to do is I'm going to move it. That'll be easier. All right, that's going to have to do. And then again, it's kind of a rough picture, so it may not come, but so we know that the sun will go from one position when you're lying straight down, and then as you get up and you're at your R plus H, which would look something like this, you get an angle. Here's the problem. I don't want to keep drawing the triangle, but you get your R plus H, you get your R, and then you have this distance D. So that's how you create the triangle. Now that I've shown you that, instead of wasting time drawing a very good triangle, we're just going to go to the nicely drawn triangle. Okay? So here we have a much better drawn triangle, and if I had a straight edge and a board and I didn't have this stupid pen, you can see what I did, the same things I did here. First you have your auxiliary angles. These are basically the given angles, right? Your first sunset where you're lying down and you see it, and then you get up, and then you see the sunset again, and you create this angle theta. All right? So when constructing this triangle, you now have this side, and you want to be able to prove, which you should be able to do, I think, pretty easily. You want to be able to prove that these angles are the same, and that's actually pretty easy to do, right? These are vertical angles, they're congruent. This angle plus 90 is theta, so you'll notice you have the same angle here, and you have 90 here, so therefore, because of the way the triangles add up, this will be equal to theta. So a little geometry will give you that this is theta, and you now have what I can draw here. Oh, you can't see you can't see the hand. Yeah. So you have this theta, these two thetas are equal, right? Because of the vertical angles. I'll do it again. And now in this triangle, you'll notice that this angle plus this angle plus this angle is 180, but in this big triangle, you have 90 plus this angle here, which is the same angle for this triangle. We don't even need to know what it is, and that means this angle must be theta, right? Because the sum of the angles of a triangle have to add up to 180. So it's a little geometry. You notice we have to pull that out. And looking at our auxiliary rays, we're able to form this triangle, and this triangle becomes obvious because it includes a side that is exactly what we are looking for, right? So so setting up that triangle is extremely difficult. But once we have it, the problem still needs some massaging. So let's take a look at the triangle itself and see what we need. So we can look here and say that we have r plus h squared. Now I can already tell this is going to be super frustrating because it's making assumptions about what I'm drawing, and it's really irritating me. This did not do this in the spring. Equals r squared plus d squared, right? And then we can write that as r squared plus h squared plus 2rh. Okay? Now, this simplifies, right? The r squareds will cancel out. So we get here that d squared equals h squared plus 2rh. So that's one thing. Now, we can make this simpler by noticing something. Let me ask you something. Well, let me ask you an unrelated question. I want you to pretend you have $100. All right? Now, I have $100 and someone gives me a penny. Do I have an appreciable more amount of money with that penny? Would I say, well, you only have $100, I have $100 and 1 penny? Is that something you brag about? No. Right? Basically, $100 plus a penny is $100. So now H is much, much less than R, right? So H squared is going to be this tiny little amount, like 4. And R, we already suspect R will be somewhere in the order of 10 to the 6th, right? So here it's worse. It's like 1,000,000 plus 4 is nobody cares. So the mathematicians will hate this because we're not doing a mathematical thing here, but we're just setting that equal to 0, and we're going to say that d squared is approximately 2rh. Okay? So this could seem problematic because we have no idea what d is. But we can look here and we have this angle theta that we made a big deal about. You might be saying, we don't know what that is either. But remember, it took 10 seconds for it to, or 11.1 seconds for the whole thing to happen. So we know that we covered some fraction of an angle here. So basically, we can set up that theta over 360, right? Because it takes 24 hours, will equal, and we're assuming constant motion here, t over 24 hours. They're the same thing. So we can solve for this in degrees right away, and we can solve for theta equals 360 times t over 24 times 36, 100. All right, so one of the things I have memorized is that there's 3,600 seconds in an hour. So yeah, 86,400 sounds absolutely right. So my point here, though, and you'll see me do this often, is we now know that theta is a number, right? We now know that theta is a number. Under t is 24 times 3,600, which will equal the 86,400 that Charmin correctly reported. And stuff is flying all over the place back here. So yeah, that's all that's there. It's not written well, but that's let me do the hand. That's 24, and that's times 3,600. Okay. So theta is a number. So if theta is a number, we can now continue to use our trigonometry, and we can say that the tangent of theta is equal to opposite, right, which is d over r. This means that d equals r tan theta, and we can then plug that into our d squared equation, so we get r squared tan squared theta equals 2rh. One of them r's cancels, and we can see that r will be equal to 2h over tan squared theta, right? Theta is a number we know. H was given in the problem. We have a solution. All right? It's tricky. It's really, really tricky. Hard parts. So I'd say the very hardest part is creating this triangle and drawing the picture. And we're going to find that that's generally the case, that they won't always be this hard to draw. In fact, they very rarely will be this hard to draw. But drawing the picture sort of solves 90% of the problem. Once you have this triangle drawn, right? 2h, this is 2h over tan squared theta. Yeah. The 2rh, the r cancels with this r squared. You see it? Yeah. So once you have the triangle, then it's trivial to get to here. I mean, you have to recognize this. That's a little hard to see because it's not mathematical. It's physics, right? Makes your life easier, and you just use it. Mathematicians would scoff. But then you have to recognize, that you'll cover a fraction of an angle that you don't know over the fraction of time that you do know. And that assuming constant motion, which is a good assumption, you can then solve for theta by comparing the fractions. Once you know that theta is a number, you can continue to use the trigonometry of the triangle, right, to get this expression. And then you can eliminate d, you can solve for d, eliminate it, and get an expression with the answer. I think it's less than that, actually. But I might have, when I looked at it, it might have been t squared. You should get around 5 times 10 to the 6th. That should be your answer. That you'll know theta is right if that's what you get. So yeah. All right. So questions about this? It's a good one to think about and mull over for a little bit. And you can see when we go over, as you're thinking about it, I'll delete this, but you're gonna get, but don't get upset, because you'll see that the next slides, which I'll let you see, just do it all very nicely, right? They have that triangle, they do the same thing, and you'll notice that it very nicely comes out. Yeah, no, you were right. So they gave us theta, 0.404625, and then we get our expression here, and you get about 5.2 times 10 to the 6th. So yeah, if you get 5 times 10 to the 6th, you're right. Okay? I think, would you agree with me? Would you all agree with me that the math itself was very simple in that problem, right? None of the math was hard, but recognizing which math to use, that was pretty difficult. And that will be the most difficult skill in this course. That's why I like doing this problem on the first day. So think about how far you got, and think about, think about where you got stuck, and try and work on that, and like sort of resonate with that, right? If you get stuck in a similar place, maybe it's time to step back and try something new, try something interesting. And if you keep failing, hey, I'm here. Shoot me a Skype, send me an email. During our discussion, our online discussion, perfect time to talk about the course. Okay? All right. 6.7 times 10. Well, we're good to an order of magnitude, I guess. I'd have to look it up. That's not something I've memorized. Is that what the table said that we looked at? That might be. If you Googled it, yeah. Well, this is pretty good for just winging it, right? You're within you're within an acceptable margin of error there. It's, as they say, good enough for government work. Okay, so that is chapter 1, and so I think you guys need a break. We don't have to take such a long break, but let's take a brief break. We did 15 minutes, and hopefully you all worked on the problem pretty well. So here's the thing about math on the exam. I usually, like, if you need to do an integral or something, I would usually give it, but I won't be in the room for the exam. So I'll just say that based on last semester, the math shouldn't be a problem. And again, since you have the answer there, since it's multiple choice, there are tricks to sussing out the right answer, even if you don't have all the math. So so the slides are not going to independently be available on Blackboard, but this will be added as a video. So so what you've just seen now is what the video lectures are. It's basically this. You can, when it's on YouTube, you can fast, you can play it slow, you can pause it, you can go back and look at it all you want. Okay? It's basically just this. That's the reason why I'm doing it this way, is because it's like, why do this again when it's already exists? Like I said, it's a few small things from the semester. There'll be some breaks in there. You can just fast forward through those. So a lot of them aren't even as long as they look. I was going to edit those out, but I think it'll just keep you paying attention so you don't, waste your time. Yeah, it's just, I think I'm just going to upload them. I'm going to do you one better, Sharman. I fully intend to have the full semesters. I'm going to try and get the first couple, at least this week and next week on, and I fully intend to have the entire semester up by July 1st. So you will be able to go ahead or behind or anything you want. Okay? Good. So yeah, so let's do 10 minutes, and then we'll come back and we'll start chapter 2. And I think if we get far enough, let's see how long it takes to get where we need to get to, because we're moving at a pretty good pace, I think. So, you know, so yeah, we'll see where we need to get to, because I know where the next lecture starts. So I'm just want to get there, and then we'll be okay. But we do have some stuff to talk about before we get there, and a problem I wanna discuss. Okay, so I'll be back at let's say 3:35. Okay. So, but this time you don't have to work on a problem. Just relax a little bit. I'm going to load up the next chapter, and then I'm going to step out. I'm going to take the attendance, because I think this is probably pretty good. So to take the attendance, I just take a picture on my phone, and then I deal with it after that. See, attendance done. Okay. Right. The modern definition of mass is not correct on the slide. And when you go and review this video, which again, this one will be up on YouTube as well, the recordings we're making now, you'll see that I cross it out and talk about it. Yeah, mass is the final base quantity to be defined in terms of the fundamental constants. I recorded my astronomy lectures. Asynchronous learning. Lectures last semester. I'm using them for asynchronous learning for my summer section. Quartermaster Armor. Using them for asynchronous learning. So reception. Good students. Yeah, okay, so that's the correct time. All right. Okay. So let's move on to chapter 2, motion along a straight line. And this is where we're really going to get into the nitty-gritty of starting to put together our definitions. Like we have our words and sort of our background structure, but we're really going to start to look at some quantities. So let's look at motion along a straight line. Oh, Lordy. All right. So what we're going to study is we're going to start the process of defining the simplest motion in the simplest way. And then what we're actually going to do is we're going to spend the semester sort of building on top of that. So you'll notice that things will feel repetitive in some ways, but that's because we're actually building more complexity into the system. The idea is to get one thing sort of known really well and then build on it as we can. Now, this is actually how physics goes all the way through the PhD level. So believe it or not, this is a course in mechanics. If you're a physics major, there's an intermediate course on mechanics, and there's another course in mechanics after that one, where you kind of cover the same stuff, but in a more in-depth and different way. So, and it's the same thing for electricity and magnetism and quantum physics and statistical mechanics. So when we look here, the first thing we're going to talk about is the kinematic, which is the classification and comparison of motions. So for this chapter, we're going to restrict our motion in 3 ways. This is what I mean. We're going to restrict ourselves to a very simple system and build upon it. So we consider a motion only along a straight line only. So that means we can go back or forward, right? But that's it. We discuss only the motion itself, not the forces that cause it. This is important because I need to minimize my email here, otherwise I'm going to get distracted. And then that happens. So again, we only look at the motion. We don't care what caused it. That can be a little counterintuitive and unsettling. A lot of students don't like that. Sometimes I don't even like it. So we consider the moving object to be a particle. So what that means is, doesn't matter whether you're a person, you're a particle. If you're a bus, you're now a particle. If you're a plane, you can tell that there's a reason I didn't go to art school, right? Whatever the, you know what? I don't even care whatever the hell this is. I thought it was a plane, but whatever the hell that is, use your imagination. We're going to look at it as a particle, all right? So whatever it is, we're going to look at it in this chapter as a particle. And particle motion we're going to study for a while. And you're going to find that it's not a terrible approximation. It's really not bad at all. And a particle is either a point-like object, such as an electron, or an object that moves such that each part travels in the same direction at the same rate. So that's no rotation or no stretching. We're going to be able to add both of those things. We're not really going to do stretching, but we'll be able to add rotation pretty rigorously by the end of the semester. All right, and that makes things interesting. Now, a few things. Again, whenever you're making something, and it's physics, right? So you're usually going to want to make a number line or a graph. And so here in this number line, when we're restricted to one line, we can either go in a positive, realize you're not seeing my hand here, a positive or a negative direction. All right? So position is the vector that tells you where you are, and it's measured relative to a reference point, right? So your reference point is usually your origin. And in the positive direction is the direction of increasing numbers. Negative is the direction of decreasing numbers. So one way to look at that is you can be in the positive direction, but all your numbers could still be negative, right? So you have to be careful. We're sort of doing what I like to think of as proto-vectors. We're not calling them vectors yet, but we're going to realize that there is a directional component here that we have to think about. And it's looked at in reference to our origin or our reference point. Okay? Now, why do I call the origin the reference point? Because origins are arbitrary. And when we look at distances, let's make some line segments. I'll show you what I mean. So I'm going to make some random line segments. Just make one like that, one like that, one like that. Okay? Now, I know we're only talking about one-dimensional motion, but this actually doesn't matter. So this still makes the point, and we don't have to know much for this to be true. So now imagine this red dot. Let's consider 3 dots here. The red dot, the blue dot, and hopefully I still have my purple dot. Yes. All right. So now when you look at all 3 of these dots, right, imagine there are numbers that describe the ends of these line segments. Now, depending on where your reference point is, right, which origin you choose, whether it's blue, purple, or red, that will change the value of the numbers at each of the ends of these segments, right? If this is 0, or that's 0, or that's 0, that's different numbers. However, if you take the difference between the number on this end and the number at this end, right, the length is still the same. This is the displacement. This is the invariant part, all right? So your displacement doesn't matter. It's independent of your origin, okay? But your position with respect to that origin will then depend on the origin, okay? So keep that in mind. I hope that makes sense. Does that make, actually, I'll just ask you flat out. Does that make sense? Is there any question on that? Do you see what I mean about the origin being arbitrary? That's why it's the reference point. You put it where it makes your life easier, or you just put it anywhere you want. Okay? All righty. Good, good. So let's go forward. Now, we just defined this idea of the change in displacement, right? Where if we look at a segment, let's draw another one. Well, let's draw a straight line segment. Let's keep it classy, San Diego. Not that we're not San Diego. We're in New York. Well, I'm in New Jersey, so I guess we're intrastate. But the displacement, whatever the number is, wherever you put your origin, you'll have some number there and some number there, some position, right? So your displacement, delta x, will be the final position minus the initial position. You'll notice they do that here, but here they're kind of asinine and call it 2-1. So you'll always see me write it like this. Delta x equals x final minus x initial. Halliday and Resnick does not like to use letter subscripts for some reason. I have no issue doing it. I think it's a great idea. I'm a fan. But I want to go through each of these simple examples so we can sort of get an idea that even though the numbers themselves might be positive, the positions might be positive, the delta x, or the change, can be negative and will give us the correct result. So if we start at x equals 5, right? So let's call this, let's make our reference point here. We'll call that 0. All right, I can get behind that. So if we start here around 5 and we move to 12, our final is 12 minus our initial, which is 5, and we're going this way, right? We're starting here and moving this way. That's positive, in the positive direction. So we expect delta x to be positive, and sure enough, 12 minus 5 is 7. But don't be afraid of these negative numbers, folks. So if we start at 5 and go to 1, we're still in the positive numbers, but we're definitely moving in this negative direction. So we should expect a negative result. And we notice that we have 1 is our final, minus 5. 1 minus 5 is minus 4. And that's the negative direction. Now, if we go from x equals 5 to x equals 200, that's way out here, and then back again, you'll notice our initial, we have 5 minus 5. We don't need to consider the 200 part, and delta x will equal 0. So the actual distance covered is irrelevant. We only care about the initial and the final. All right. Does that make sense? Everything, those three simple examples of displacement? Good. Does anyone have any questions that are burning? They feel like they want to ask? Well, they can't be that burning because you haven't asked them yet. But still, if you want to ask them, now's the time. Oh, good. Burning question. If there's a final initial, there is no work of middle one? No, I don't know what you mean. If you mean work like we mean work, we haven't introduced like work in physics. Work will be a term. But this doesn't matter, right? Because we just want to know in our process, we go from 5 all the way out to 200. Let's say that's here. But then we go all the way back to 5. So we only care in this displacement what our final position is, which is 5, and our initial, which is 5. And you'll notice we came back to where we started. So there's no displacement. It doesn't matter that we moved one way. We came back. Now, if we cross this off, right? If we had crossed this part off, that would be a whole different. That'd be a whole different story, right? Then you'd have your final would be 200, and you'd have to do the whole thing. But whatever you're gaining by going forward, you're losing by going back. Okay? Cool. All right. Displacement is fun. All right. So they do talk about vectors here. That's surprising. So displacement, because it has a magnitude and direction, will be called a vector quantity. All right. So it'll have the magnitude, which is that length of distance, right? In this case, meters or feet, and then the direction, whether it's positive or negative along that number line. So if we ignore the sign, or we take the absolute value, is a better way to think of it, we get the magnitude of the displacement, which is the distance. All right. So the magnitude of -4 here is 4. So here we have a checkpoint, and I want you to sort of work on this one. Position is not a vector. Displacement is a vector. Position is a scalar. Okay? We got to be careful. Yeah. So here are 3 pairs of initial and final positions, respectively, along an x-axis. So the first thing we're going to do, almost assuredly, is draw an x-axis. Everybody loves the x-axis. We're going to have some, so we're probably going to want to put our 0 point here. So now the question is, which pairs give a negative displacement? So you have initial and final. So you start at -3, you end up at 5. You start at -3, you end up at -7. You start at 7, you end up at -3. Which ones are going to be not great? Or negative, rather. Negative has such a negative connotation to it. It's not great. I think definitely. So remember, if you're struggling with it, right, delta x, the displacement, is going to be equal to x final minus x initial. Okay? Right. Vectors always have both a magnitude and direction. That is correct. Absolutely. So if we look at A, right, the initial is -3, and we have 5. So x final is 5 minus 3, which is going to be 8, right? 5 minus is plus. So A is not negative, so that won't be one of our answers. Let's look here at 7. So we start off with minus 7 minus 3, right? That's going to equal minus 4, right? So when we get there, we start off at minus 7. Here, the value of the displacement will still be negative, but our direction, because we still live over here, right? So this one is going to be, this one's kind of fascinating, because even though we have minus 4, we start at minus 7, or no, wait a minute, hold on. We start at minus 3, right, because this is the initial. So we start at minus 3 and we end at minus 7. So this isn't weird at all. That's negative 4. That's fine. Yeah. Remember, these are the initial values, right? So we start at minus 3. We're ending at minus 7. We are going this way. That is negative 4. So B is negative. And then when we look at here, we have our initial. We go for C, we start at minus 3. Or no, our initial is 7, right? This is how I know I've been up too long. I'm messing this up. So our initial is 7. So we start at 7, and then we go to minus 3. And I know exactly why I'm messing it up, because minus 3 is the initial here, and it's the final here. And my brain has a thing where I switch things like that. So I even know why I'm messing it up, because my brain is flipping it, even though it's not flipped. And that sucks. So yeah, we can start with 7. And along the number line, we are going negative to minus 3. So we have our initial is, our final is minus 3, minus our initial, 7. That's going to equal minus 10. All right, so C is negative. So B and C are the correct answers. Does everyone see it? Good, good. All right. See, there we go. There is the answer. Now we get to some fun times. So we have the average velocity is a ratio of the displacement to the time interval for which the displacement occurred. So the average velocity in a process is equal to delta x over delta t is equal to x2 minus x1, t2 minus t1, or the way I like to look at this is v average equals minus x initial over t final. It's not letting me do my curves, which is really irritating. I don't like that it's making assumptions about what I want to write, and I don't like that at all. Not really coordinated enough to not see. You're going to have to see that that's an F. It changes it, and I can't really do much about it. T initial. Okay. So I wonder if it's just the stylus. No. No, even the mouse sucks. See, it's still, that's what makes me think that it's not the stylus at all. Just the mouse is, and this is all very, what a difference 2 weeks makes. This is ridiculous. Ridiculous. So, Um, okay, so ignoring the squiggles here, you can look at this as x final minus x initial over t final minus t initial. Now we want to be careful of this word average, and I don't want to sort of give away the being careful of it, but think about how you usually see the word average, take an average of a quantity, and think if this is the same thing, all right? But average velocity has units of distance over time, meters per second. No! The armadillo has been, the graph is, I just want to be sure I'm not missing anything with that graph. Hold on. I hate that they've done this. All right, so basically, you can see here this is an x versus t graph, and the average velocity is the slope of the straight line that connects any 2 points. So when you look here, if you take any 2 points and connect the slope, that will give you the average velocity between that position and that time. So a positive slope means a positive average velocity, and of course a negative slope means a negative average velocity. So we can find the average velocity by comparing the slope or the rise over run of the armadillo. So if we start here at 1 point and go up, we'll notice that the delta x here is 6 meters over t equals 4 minus 1, 3 seconds. 6 over 3 is 2 meters per second. So that would be the average velocity of the armadillo. You'll notice that it's not the instantaneous velocity. The instantaneous velocity would be the tangent along any instantaneous point on the curve, which should look hauntingly familiar to you from your Calculus 1 course. Hauntingly familiar. Spooky in a way. So average speed is just the magnitude of the average velocity, and it'll just be the total distance over delta t. Okay? Average speed is always positive, and it has no direction. So if you get the average velocity of minus 3 meters per second, your average speed is just the absolute value of that average velocity. So I think I want to write that down and say that S average is equal to the absolute value of V average. Now again, I want you to think, is this how you normally see average? The answer really should be no, but I want you to think about what you're doing between those there, why we call this average speed. All right, so now we have an example that we want to do, which is you drive a beat-up pickup truck along a straight road for 8.4 kilometers at 70 kilometers an hour, at which point the truck runs out of gasoline and stops. Over the next 30 minutes, you walk another 2 kilometers farther along the road to a gasoline station. So we're gonna want to solve this and sort of look at each part of this. And I'm gonna do this one. So the thing is, we want to know what's the overall displacement. So we want to make a sort of a small picture of what we have. So I'm going to make a straight line. So we know we go 8.4 kilometers, right? And then we run out of the gas, and then it says you walk another 2 kilometers to a gas station. So let's change colors. Say we walk another 2 kilometers to a gas station. So when we look here, when we do this, right, we want to know what is your overall displacement. So we know that this is 8.4 kilometers. And we know that this is 2 kilometers. So all we have to do is add them up, and we get delta x is equal to 10.4 kilometers. That's not so bad, right? So we want to look at that. And then we want to get to part B. So it says, what is the time interval from the beginning of your drive to arrival at the station? Well, it won't let me save it, unfortunately, but if you look at what I did before, right, we'll start at 0. Hold on, I'll make the straight line again. We have these two distances, right? First we went 8.4 meters, and then we go we walk another 2 kilometers, right? We're both in kilometers, so if this is 8.4 and this is 2, the total displacement from beginning to end is just 1 plus the other, right? It's 8.4 plus 2, so that's 10.4. So we actually got 10.4, not 10. I just want to be clear there. So now let me see what it asked. I'm going to just ask the other questions. I don't want to delete the given information because normally I would have a whole board where this would be up and I'd write the given stuff. So the next thing it wants to know, what is the time interval from the beginning of your drive to your arrival at the station? Okay. So if we want to figure that out, we know that delta x equals, or no, sorry, hold on. I want to this is how I know I'm getting tired. We have V average equals delta x over delta t, right? So we know it took 30 minutes, or we know that delta t here is equal to 0.5 hours, right? Half an hour, 30 minutes. And so now we know we have the speed here. So we have 70 kilometers per hour, and we have delta x. So we just have to switch it, and we can get delta t because of math equals delta x over V average. All right. But we don't have V average there, do we? So it asks for our overall. No, right. We do. We have velocity there. I'm getting ahead of myself. So we have this velocity, and we can look there and say that we have delta x is 8.4. Over 70. Does anyone have a fancy calculator? Yeah, I'm doing B. So the B is, again, what is the time interval from the beginning to the end? So it wants to know what's delta t for the whole thing, right? It wants to know this delta t, and we have delta t2 here, so we need to figure out delta t1, right? Okay, so when we can do that by someone's got to have a fancy calculator. I guess I can open up mine. I'm way too tired to do this in my head, which I usually do. It can be pretty impressive sometimes, but one must know their limits. I'd be sitting here second guessing everything. 8.4 divided by 70 equals 0.12 hours, right? We have to be careful. So our total time is going to be T1 plus delta T2. All right? So let's look here. And we have delta T1 plus delta T2. And that is going to be equal to 0.12 plus 0.5 equals 0.62 hours. Now you can convert that to minutes or seconds if you'd like. It's up to you. And you might need to do that, but that's easy to compute. Okay? So now for the interesting question. So what is your, so let's see here. We have delta T, we have X, right? We know this is 8.4 and this is 2. Now we know this is 70 kilometers per hour. And we can sort of guess here that we have 2 over 0.5. So 4 kilometers an hour here, right? Now I have a bet with a colleague that I'm reworking this class with, or a research partner of mine, really, per hour. So I have a bet with him. He thinks you're all going to mess up this problem. I think you guys are going to get it right. Or I think most of you will get it right. So don't let me down. Given all this information, and given the definitions we've discussed, what is the average velocity from between the start of the journey and the end of the journey? I want to give you some time to figure it out. A couple minutes at least. The question is, if I give you the question, you lose all the work, right? So that's not helpful. The question is, what is the average velocity? That's it. There's nothing insightful there. It's just, what is the average velocity between this point and this point? Yo, you guys are killing me. All right, so I lost the bet, it would appear. So remember, what you're doing is you're taking the average of the velocities. That is not what it asked. It asks for the average velocity, the average, which is equal to delta x over delta t, period. This is not an average of velocities. V average is going to equal the total displacement, which is 10.4 over the total time, 0.62 hours. And then 16.7 kilometers per hour. Damn it. Now I'm going to have to assign that problem for our discussion. I thought I was going to get away with it. So hurt. So hurt. That's all right. I'll get over it. Do you see the difference where the mistake is? Does that at least make sense? Okay, good. So you want to be careful and use the defined terminology. Average, it's the average velocity, not the average of the velocities. Okay, those are two completely different things. But I did write that 4 kilometers a second to mislead you. Okay. All right. So that part D is you can do on your own. I'll let you read it. We'll pause. So read that, and if you have issues with it, we'll talk about it on our live segment, our discussion segment. So we'll save that for discussion. But you'll notice they're just adding more to it and having you practice it again. Okay? So now we want to look at not average velocities, but instantaneous velocities. And remember, I told you it should be a exciting callback when we talked about the definitions. So if you look at the average velocity, right, and this should make some sense. X final minus X initial over T final minus T initial. One thing to realize is that the position itself will and can be a function of T. So another way to write this is X final of T minus X initial at T as functions of T over T final minus T initial. Now when you draw it like this, it's highlight. I hate when it does that. When you draw it like this, it should look immediately from calculus 1, it jump out at you. If you take the limit as delta t goes to 0 of this quantity where x depends on t, you will get the derivative dx dt. This is the according to Hoyle textbook definition of a derivative. All right. Well, according to Stewart textbook definition of a derivative. All right. And again, you look at it by looking at, you can think of it as taking a bunch of small average velocities and shrinking them, right? Smaller and smaller and smaller until you get the velocity at one point. And that's your velocity at that instantaneous point. All right? So the velocity is a vector, instantaneous velocity is a vector, and it can be determined by taking this time derivative with respect to t. Okay? Now, speed is the magnitude of instantaneous velocity. So a velocity of 5 meters per second and minus 5 meters per second will both have an associated speed of 5 meters per second. All right? Now, the following equations, we'll do this checkpoint, give a position, you'll notice the way I wrote it, x of t, of a particle in 4 situations. In each equation, x is in meter, t is in seconds, and t is greater than 0. We don't go back in time. This isn't the Avengers. So you'll notice you have situation 1, 2, 3, and 4. So now, A, in which situation is the velocity of the particle constant? All right? So you have x. The instantaneous velocity v is equal to dx dt. So now what A wants to know is which one of these is constant. So I'm going to write them 1, 2, 3, 4. It's going to be A, B, 1. All right, we'll just put check marks next to the correct one. So let's see. All you have to do is evaluate that derivative, right? So is 1 the only answer? So we look at this. The derivative is going to be 3. 3 is constant. So 1 looks good. What about 2? 2, when you take that derivative, the derivative of 4t is going to t squared is going to be minus 8 times t, right? So is that constant with time? Nope. So 2 is not one of our answers. What about 3? Also, nope. We're getting there. You're rushing ahead of me. So 4, what's the derivative of minus 2? 0. Is 0 a constant? Sure is, right? Sure is. So we have, so we have 1 and 4 are constant. So now B is in which of these is V in the negative direction? Well, that's interesting, huh? So remember, T is always greater than 0. So we have V is constant at 3 here, right? So it's not going to be that one. When we take the derivative here, it's minus 8t. Is there any value in which t that makes x positive? Take a look. I see some people are answering. All right. So it's always going to be minus 8t, and t is always going to be positive definite. So therefore, the velocity will always be negative. All right. And we can see with 3, we're always going to have that negative. When we have t. So I have a little. So I don't like the quotient rule. So I usually write these things. I would write 3 as x equals 2 times t to the minus 2. And then I'm just happier, and I don't have to use the quotient rule or figure it out or be bothered by it. I'm just not a fan. It saves me a lot of time and energy. And writing it this way, it becomes very obvious that t will, in the derivative, will indeed be negative. So you have 2 and 3. And then 4, it's 0. 0 is not negative, so it's not true there. So we have 1 and 4 for A and 2 and 3 for B. And that's what a lot of people have answered. So it seems that we are correct. Okay? All right. So let's keep going. So we have some interesting examples here that show position versus velocity. And we can see here the graph shows the position and velocity of an elevator cab over time. So we see the position, the slope of x of t, and also the velocity is 0 from 0 to 1. And from 9 seconds on. And during the interval B to C, the slope is constant and non-zero, so the cab moves with constant velocity. So we can have that situation where the velocity is constant, right? Where we're moving up this linear section here. And then we have this rise over run. So now we want to move on to acceleration. Now, acceleration is a non-intuitive property. I always describe acceleration as what makes you puke. And we'll sort of see that as we go forward. In this case, if you've ever been on a fast-moving road or a throughway or expressway, you really feel acceleration when you enter or exit the expressway, when you're speeding up or slowing down. When you're cruising, even if it's a really fast speed, you're not accelerating. So acceleration is what makes you puke, and acceleration is generally what kills you. All right? And you'll notice that acceleration is defined, the average acceleration is defined as the change in velocity over the change in time. And since velocity is a vector, this makes acceleration a vector. And our instantaneous acceleration, because we have the same form that we did, which is the delta of a quantity that depends on a variable over the change in the variable, we can take the limit as delta t goes to 0, and we get a equals dv dt, the instantaneous velocity here. All right. Now these relationships, so you'll notice that you have v equals dx dt, right? And dv dt equals d2x, the second derivative with respect to t, but that is going to equal to the acceleration. All right, so the acceleration is a first order differential with respect to v and a second order differential with respect to t, all right, in position. Okay. So, I love it when I get ahead of them. So they've just done the chain rule and done everything here and talked about acceleration being a vector quantity. Now, one thing you want to notice is that the acceleration and the velocity need not point in the same direction. So be careful of that. If the signs of velocity and acceleration happen to be the same, the speed of the particle increases. If they're opposite, the speed decreases. So those are your two limits there, your two limiting cases. And you'll notice here that we have hold on, I just need to recapture my brain, sorry. So you'll notice we have the units of our acceleration are going to be meters over second squared. So meters per second, okay? And that's what they have here. All right. So if a car with, let's look at this example really quickly. If a car with velocity of v equals minus 25 meters per second is braked to a stop in 5 seconds, then the acceleration is equal to 5 meters per second. The acceleration is positive, but speed has decreased. Let's see if we can actually see that happen. All right. So we have a car with a velocity of minus 25 meters per second. And then we have, it goes to a stop 25 meters per second. That would be v initial. And then it's brake to a stop in 0 equals v final. And this all happens in 25 seconds. So, or in 5 seconds rather. So we have A is going to equal 0 minus 25 over 5. That's going to give us our plus 5 meters per second squared, right? Meters per second squared, that's what I've written. So the acceleration is positive, but the speed has decreased. So you'll notice that we talked about the signs, right? The velocity and the acceleration are in opposite directions. Therefore, the speed will decrease. So that's an example of that last point that we made. And it's important. We've gone through a lot of points today. And I know, I wish we, I mean, I was tempted to stop a while ago, but it's summer school. We got to push through. But I hope you can see that point. It's a little subtle, right? It's the signs that are opposite. That means it's decreasing. Or when they're the same, it's increasing. All right? Not the values themselves. Now, we want to note that accelerations often are expressed in terms of units of g. 1 g is 9.8 meters per second squared, and a unit of g is the acceleration due to the Earth. All right? We're going to talk about that and expand that a lot more in our second lecture. So let's talk about our wombat and see if we can get some clarity here with what's going on with our wombat. So a wombat moves along an x-axis. We want to know what is the sign of its acceleration if it's moving A, in the positive direction with increasing speed, B, in the positive direction with decreasing speed, and C, in the negative direction with increasing speed, and D, in the negative direction with decreasing speed. So you got to read those because I think I said that increasing is decreasing, and that's okay. So see if you can figure it out. See what you come up with. The way to make this easier, believe it or not, it may seem counterintuitive, but is to draw a line, right? To draw a line on your x-axis and ask yourself what's happening. So let's look at A. I'm moving in the positive direction and my speed is increasing. So I'm moving faster, my acceleration is going to be positive, right? So that's clear. And then in the positive direction, but now I'm moving in the positive direction, but now my speed is decreasing. So if my speed is decreasing, I have to be accelerating in the opposite direction. So this one will be negative. All right? Think about it. As I go forward, I go slower and slower and slower and slower and slower till I stop. That's indicative of the acceleration moving in the opposite direction. So I'll do those two for you, A and B. Oh, now I gotta draw. A is positive, B is negative. All right, now try C and D using the same logic. Well, let's take a look. So you're going in the negative direction, right? If you're going in the negative direction, you're increasing speed. Which way are you accelerating? Is your acceleration going to be not negative or positive? Positive. All right, let's take a look at it again. Remember, positive and negative indicate direction. I'm going to do A and B again, actually, to sort of make my point. If I'm going along the x-axis and I'm increasing, right, this is the positive direction. So if I'm increasing my acceleration and going this way, my acceleration will be positive. But now if I'm going positive and slowing down, that means I'm not being accelerated forward, I'm being accelerated in the opposite direction. So the acceleration points the other way. Now, if my acceleration, if I'm moving this way, right, and I'm accelerating, I'm going faster, if this is positive, is this the same acceleration as the other one? No, right? So this has to be negative because the other one is positive by definition. So we have to have that C is negative. All right? Just select, I already had the pencil selected. C is negative. Yeah, absolutely. So remember, so C makes sense, Sherman, when we look at A. So with A, and I'm realizing now no one can see it because I don't have the hand. Sorry about that. With A, if we go this way and we move faster, that's positive, right? So now with C, we're moving in the negative direction, but we're increasing speed in the negative direction. So if this one going faster is positive, going this way and faster is not the same motion, right? It has to be negative because they have to be opposite. If if they had the same sign, they would be identical, if that makes sense, right? You'll notice that makes sense with B. If you're going positive and slowing down, it's like you're being pulled in this direction, in the negative direction, right? That's for B. So for C now, you're just going this way but speeding up. Right. Well, yeah, exactly. Yeah. If you go in reverse, if you push that button in reverse and you speed up, you're going in a negative direction. Does that make sense? It's good to stop and talk about this stuff. I'm more than happy to do it. Good. So now what do you think about D? So now with D, you're moving in the negative direction, but now you're decreasing in speed. Good. So it has to be, if it's decreasing, it's the acceleration is pulling you back in the positive direction. So D will have to be positive. Very good. I think we struggle with that because I did not have the hand on. So sometimes you'll have to remind me of that. That's okay. All right. So we still have a little bit more to go, but I think we need a break. I think I need a break, to be more precise about it. So let's, so again, I have us down till 5:30, and I kind of said we'd need the whole time. I was hoping we wouldn't, but I really think we do, because I want to get to the right point, and we are almost there, but we will need about another half hour or so, half hour to 30 minutes. So let's take a 15-minute break, and we'll come back at 1:45, and we'll finish on out, okay? Oh, that's okay. Well, I hope you understood it here. Oh, well, then I feel good about it. I'll give those kudos to me. It'll still be a bit of a journey, though, Liquan. It's good to understand the difference, but then actually applying the difference is another step still. But you'll get there. That one's about practice. You know, that's where it's very much a journey. Very much a journey. But I'm glad you could take a step. It's always a good feeling. It's always good. All right, I got to get something to drink because my throat is parched here. So I will be back at about 1:45, and we'll finish out, okay? Remember, Charmin, I don't want to quite do 30 because that would take up too much time, but I am recording this, so I will put this on YouTube, and you can see what you missed tomorrow or the next day. I just have to, it'll be a little clunky getting it set up. Once it's set up, though, it'll be smooth sailing. I have the other lectures ready to go. I think I was going to, like I said, I was going to edit them, but I think I'm just going to dump them on YouTube, and it'll be fine. You know, you guys will know what to skip or know when I'm being ridiculous about something. So yeah, we're still recording, so we're still good, and you can see it then. But we'll definitely take 15 minutes, and maybe even a little longer. Okay. All right. Oh, I'm gonna go away on the thing. Hold on. Okay. Hopefully your brains are a little. I'm here. I'm here. I thought I'd give you a little more time. I'm whatchamacallit. My brain is a little more mush than usual. Um, so, but we are on the home stretch. So we're only going to section 2.4, I believe, and yeah, that'll be our last section. But we do have to cover 2.4 because that's where we stop. That's where the next lecture begins. So we got to get there. Okay, so we just got to stick it through and be brave. But that's all right. 40 minutes is enough time to get there, and that's about when we would end. So now imagine we're supposed to go, like if we're in class, 5:35 is when lab ends. So if we were in there, we'd be from 10:35. You'd have 2 more hours of lab after we'd basically done this part. So keep the time is no joke, no joke. So let's go on. You see that? Now we can also look at our velocity graph and see the acceleration graph. All right. We notice we have this interesting looking acceleration about what you would feel with your acceleration and deceleration. I'll let you look at this to get what's going on because I really do want to move on to constant acceleration. So we saw the relationship before where we have, in general, for almost all cases, we have A, we have some position versus time, x of t, and v will be equal to dx dt, and A will be equal to dv dt. Now this will always be true for all x of t. All right, but we will sometimes make a limiting case to get explicit functions, right? This is very general. So when the acceleration is constant, we're going to say A is equal to constant. All right. So now when we do that, to solve for v, will be equal to the integral of A dt, and x will be equal to the integral of v dt. All right. So again, where we went in general, starting with x and taking derivatives to go from A, if we constrain A to be constant, we can integrate or anti-differentiate back up to get v and then to get x. All right. And when the A is constant, this will be very simple to do. So let's take a look. Now, no, it doesn't have to be increasing at a constant rate. What I mean by A is constant, if A is equal to some constant, that means that dA dt is equal to 0. All right, it's just, it doesn't change in time. It could be positive, it could be negative. And the acceleration itself is not increasing or decreasing at a constant rate, it's just constant. The velocity might be increasing at a constant rate. So the velocity might be getting bigger, but the acceleration would be just the same, right? So to look at it graphically, if an acceleration is constant, it would just look like a straight line here. And you'll notice the value doesn't change with respect to time. So if AT is equal to, say, 5 here, it will be 5 for all time, right? But now when you take the integral, when you integrate up to get to the velocity, so you do that by taking a dt integral. I'm just going to write that like this. You'll notice here, with that constant acceleration, the velocity is increasing with time, right? And of course, the slope is the acceleration, and that's the change in velocity. So here you have a t to the 0 term, right? Anything to the 0 power is 1. Here you have a t to the 1 term. Oh, yeah. Well, let me draw this first, and then I'll do that. And then you have a squared term if you integrate up here. Again, if we do another integral of dt. Now I'll do the hand sign. So again, looking at it, you have t to the 0 power here, right? And t to the 0 is 1. When you integrate up, you'll have a linear term, t. When you integrate up again, you'll have a t squared term as your dominant term. So you'll notice that x depends on t squared, and v will depend on t. It'll be linear, and your acceleration will be constant. It will not change value as t goes, right? So what I said before was that if the acceleration is equal to, say, 5, right, then it's always going to be 5. The acceleration doesn't change. But the velocity will change, right? It'll change with t. So constant acceleration occurs very frequently. In fact, there's a lot of, you'll be surprised at how many situations have common acceleration is constant acceleration is a very good approximation. So we want to note that constant accelerations means that velocity with a constant slope and a position with a varying slope unless a itself is equal to 0. All right? So for these cases, 5 special equations can be derived, again, by taking that explicit integral. Okay? And I want to see if I have space on the next page because I also just want to do this myself. I want to see what asinine thing they're going to come up with. All right, yeah, I don't like how they do this. So let's do it here. All right, so if a is constant, I'm going to do a lot of drawing here now. If a is constant, v will be equal to the integral from t initial to t final of a dt. Now we usually always start dt. Actually, I'm going to leave this as an indefinite integral for important reasons. We usually always start this constricts us to a very specific solution where we want a more general solution. So we're gonna look at this, and the integral of, and now a is constant, right? So we can actually move a outside the integral. So let's move that a outside the integral. Hold on. Right? And so this is now going to be equal to v is going to be equal to a naught, or a times t, right, plus a constant of integration. Now the constant of integration is just going to be the initial velocity, right? The velocity at t equals 0. So you plug in t equals 0, you have some initial velocity. And then you get v naught is equal to a times t. Now, if you integrate to get the position, and you'll notice that this is exactly what we expect. Some v naught, right, at t equals 0. You can see that in the y-intercept here. And then we have a straight line with slope a. That's exactly what we have. And now to get, when we get x sub t, right, we can write that x is going to be equal to the integral of v dt, right? And that's going to be equal to the integral of v naught plus at dt. So we're integrating by terms. We have v naught t plus 1/2 a. I really needed to not do that. That is really irritating. It's like, oh, hey, let me screw up what you've written. AT squared. All right? And you'll notice that, again, we have a constant of integration plus x naught, and so that's going to be x. Another way you'll see this more commonly written is as x naught plus v naught t plus 1/2 a t squared. All right? So those are how we get 3 of these 5 special equations, all right? Or at least 2 of these 5 special equations. We'll see some of the other ones as they're derived, but this is essentially the calculus you do to get from these equations to here. And you'll notice that everything lines up. It's weird, I went from down to up because we start with the bottom graph and work our way up. If I started with acceleration, none of this would line up very well. So the first basic equation, we know exactly how we got it. We don't need to listen to their crazy talk. And we got this by taking the antiderivative. So I'm comfortable here that we know how this one was obtained. Yeah. So we know how this equation was obtained, right? We have to, so we do have to know how it comes. Yeah, you absolutely have to know where the equations come from, because you'll be applying that to every situation throughout the rest of the semester. This is what you're doing now is you're using a specific set of assumptions, which is that a equals is constant, and then getting the specific solutions for that case. So very much so, you really do. That's one of the skills you do need to know, is how acceleration, velocity, and position are related to each other, and given one of those functions, get the other 2. You absolutely have to know how to do that. That is a big time skill here. What's also, we're going to focus, though, a lot on constant acceleration. And it's really unfortunate because a lot of people will call these standard equations. They're not standard in any sense of the way. They're the correct equations when you assume that A is a constant. Okay? And when A is a constant, you can take that integral of that constant A and get this equation. And I'm not going to give them any more fluff there than that. So you'll notice you take the integral again. Again, I'm not sure exactly what they're doing here. I think they're just trying to massage it with algebra. But you can just take the antiderivative of the equation we had before and get this equation. You'll notice my equation, I just added the x naught to the other side. That's all I did. That's simple algebra. And so by using that integral, you get this equation. Now, when you have those 2 equations, what you can do is you can notice a few things. One, if you have the average here, right? The average, x can be expressed as x naught plus v average times t if a equals 0, right? If there's no acceleration. So if you have this equation for v average, I guess they're getting this equation here, but basically with the first 2 equations, you can actually eliminate t. Oh, I see what they do here. Once you have the, they were doing an algebraic trick. We should just use calculus. There's no reason not to use calculus. It makes things easy, straightforward. It always works. Their way of doing it seems very specific to constant acceleration. Additional useful forms, you get these by algebra. So for instance, this one you'll use frequently. The first 2 equations, you eliminate t. So it looks like in this equation, you eliminate a, and then you eliminate v from one of the other equations. You can probably solve those and eliminate something for v. And so these equations here round out your 5 kinematic equations of constant motion. And I believe, or constant acceleration. And I believe you have, I want to get to this part here. You have this table that shows you what your missing eliminated quantity is and what your corresponding kinematic equation is. So if you're not given t and you're given a bunch of stuff, for example, and you need to find an acceleration and you're not given t, you'll want to use this equation, right? So you can use this table to solve for any, you can always eliminate one quantity, and then you only need the 3 others to solve for a fourth. All right? So, and again, you'll notice it says make sure the acceleration is constant. And that brings us to our final activity of the day, which is our checkpoint. We're going to start this very next class starts, or lecture starts, going over this table. All right? So you should be in good hands from past me. Now, the following equations give a position, x of t, of a particle in 4 situations. Which of these situations do these equations, or 5 equations, apply? So which one of these has constant acceleration? Again, 4 situations. Which ones apply? So 1, I would say definitely, right? If you take the second derivative of 1, you get 0. 0 is constant. The acceleration is constant. What about 2? What's the second derivative? Will the second derivative of 2 lead to a constant function in time? No, right? Because we have that third power. We have that third power here. So the second derivative of that part will be equal to, 3 times 5 is 15, times 2 is 30t. So this one's a big no. What about 3? Well, we can see right away that we have those 2 to the negative t's, so that's just not going to work. What about 4? 4, yes, right? If you take that second derivative, you have 10, right? 10 is constant, so 4 will be able to apply. And that's why it's important to know what's in general, because these equations don't always apply. And you have to be able to identify when you can use them and when you can't. That's super important. That's one of those things that you will literally be tested on, right? Is when you can use these equations and when you can't. That you have to know. All right? And that's good physics. That's important physics. When you can use, part of this is learning these when to use your math as tools, right? So you have to know when you can use a tool, when you can't use a tool. It's a very critical skill. Okay, I am pooped and we have caught up, so I'm going to stop recording.